I want to talk about finding partial derivatives given a contour plot. So let's say instead of giving an equation of a two-variable function, all we have is the contour plot of the two-variable function. So again, the contour plot is a two-dimensional representation of some three-dimensional object. And each of these curves is a level curve that have the exact same height, or z value. And in this case, we see by the labels on the z values that this curve has a height of 5, and as I move towards the left, the heights of these curves get lower and lower. So we could think of this as some sort of downward sloping valley, is what the three-dimensional picture looks like. So looking at this contour plot, let's say that we were asked to estimate the partial derivatives. Estimate has an S in it. Estimate a partial derivative f sub x evaluated at the point, let's pick a point, something like this. No, let's pick a more interesting point. We're going to pick a crazy point, like this point. And let's say that this is the point 2, 3, approximately. So I want to estimate my partial derivative with respect to x at the point 2, 3. I don't have a function, so I'm not going to be able to actually compute the derivative, but I want to know graphically, what is this asking? Well, recall that partial derivatives with respect to x are asking, what is the slope of the tangent line where that line is traveling in the x direction? That's one way to think about it. I'll write this maybe in green. Another way of thinking about it is to say, what's my change in height as I change x by a little bit? So my x values are going to change a little bit, the y's stay constant, and I want to know how does the height of my function change as I change my x values a little bit. And at this point along this curve, we see that as I change my x values a little bit, it looks like my heights are increasing a little bit. That as I travel from the curve z equals 2 to z equals 3, over this entire length, my heights are getting bigger. However, this is where it's the tricky part. Maybe I shouldn't have picked such a tricky point to start with, but you guys are up for this. So notice that if I travel in this direction, my heights are getting bigger. If I travel in the other direction, my heights are also getting bigger. I picked a tricky point because it looks like my line here, as my x values change, it's exactly tangent to this level curve. That right at this spot, it looks like tiny little steps in the x direction aren't going to actually change my height very much, because I'm walking right along this level curve that's given by z equals 1. So if I really am walking right along this level curve where z is equal to 1, right at that tiny zoomed in spot, it means that my height isn't actually changing as I change my x value by a little bit. And that's what my partial derivative is. It's actually a limit, right? As my partial derivative is just saying a tiny change in x. How does that affect my height? It doesn't affect my height at all. I will stay walking on that level curve. Maybe an easier one to interpret graphically is to look at what is my partial derivative with respect to y at the point 2, 3. In this case, it's really clear that my heights are changing. As I travel along this line, as my y values change, my z values are also changing. And it looks like right at this point, I'm at the z value of 1, but as I increase my y values, my z values are dropping. My z values are getting more and more negative. So three-dimensionally, as I walk along this line, as my y values change, my z values are getting negative. So one thing I can say with confidence is that my partial derivative with respect to y is less than 0. If I were to estimate the actual value, I could look at the average rate of change. As I go from 3 to maybe 3.5, my change in y, so maybe I'll write this out. As my y values shift from 3 up here, which I'm saying is 3.5, maybe I'll write it like this. F sub y is about equal to my change in height divided by my change in y values, which in this case, my y values are shifting by an amount of 0.5 as I go from 3 to 3.5. And my z values are going down by 2. So in this case, if I were to approximate this, it looks a little bit like my slope is about equal to -2 divided by 0.5, which is -4. So this is an approximation of what my partial derivative with respect to y at the point 2, 3 is giving me. I'm changing my y's a little bit, and that's resulting in my z values going down by 2. My final topic for today is higher order partial derivatives. So just like with single variable functions, you can take a derivative once or twice or 3 times or as many times as you feel like it. You can take multiple derivatives. In fact, we use a second derivative test in order to be able to tell the concavity of single variable functions. That's a preview of things that we'll see later. We can also take multiple partial derivatives. So we talked about how if I take my partial with respect to x, one way to write that is f sub x, or a derivative of f with respect to x. Let's say that I want to take that derivative with respect to x a second time. Then I might write that as f sub xx, the second derivative with respect to x. And notationally, I'm taking another derivative with respect to x. So I'm taking the inner derivative first and then the outer derivative second. It doesn't matter, they're both x's, so you get the same thing. Another notation for this is d squared f dx squared. All of these 3 things are the same thing. They're just different notations for representing a second derivative with respect to x. Similarly, I can look at a second partial derivative with respect to y, which is going to be written d sub yy, or dy parentheses df dy, which is d squared f dy squared. You could have told me that, right? You would have guessed this, given what we did with x's. However, the notation does get very convoluted and tricky when you start taking derivatives with one variable and then the next. So let's say that I take a partial derivative with respect to x, and then I decide to take a partial derivative of that thing with respect to y. So what's going on here? First, I'm taking my partial derivative with respect to x, and then I'm taking a partial derivative with respect to y. So my notation is df dx on the interior, because that's what I compute first, and then the derivative of that with respect to y. And the problem in notation comes from the translation of this into this final Leibniz notation, which is d squared f dy dx. This is where I'll write in red. So notice how the left to rightness of the x's and the y's switches. And I'll write in a star. Both of these notations mean the derivative, maybe I should say, derivative with respect to x first, then with respect to y second. And then finally, we can take a partial derivative with respect to y first, and then with respect to x, and our notation is exactly the opposite of what we saw above. So again, we're taking the derivative with respect to y first, and then x. That's why it's in the interior of the parentheses. And our final Leibniz notation is df squared dx dy. These are all d's, even if they start looking sort of crazy. So this is the notation for multiple derivatives. And if we wanted to, we could continue this and we could take a whole bunch. Like maybe I'll take a partial derivative with respect to y, and then 2 with respect to x, and then maybe 1 with respect to z if I had a z function. the notation for this is going to be really, really clumsy. The first thing that I do is df dy, and then I'm going to take this partial with respect to x, and then that partial with respect to x, and then that partial with respect to z. And if I wanted to write this out, I'm taking how many partials total? 4 of them, so it's d to the 4th of f of starting with, whoops, there should be a d there. The dy is the one that's furthest to the right because it's the one that we do first. dy dx squared dz. This is a crazy notation for this. I would probably stick to this notation just to save a lot of pen. So let's see an example of computing a higher order partial derivative. Really, it's not very difficult now that we've talked about taking partial derivatives. So, for example, let's say that I have some function f of xy is equal to x squared y minus the sine of x. And I want to know what's the partial derivative with respect to x and then y. That's what I'm trying to find out. Well, first, I'm going to do this step by step and say my partial derivative with respect to x, I'm treating y as a constant. So the derivative of x squared, where y is a constant, is going to be 2x, and the constant comes along for the ride. The derivative of sine is cosine, so this becomes negative cosine x. So once I've taken my partial with respect to x, I'm now going to take a partial with respect to y. So because I'm taking my partial with respect to y, now I'm treating x as a constant. When I treat x as a constant, this 2x is just a constant that goes along for the ride, and the derivative of y times a constant is just going to be that constant. And the derivative of cosine of x, well, x is just a constant. So the cosine of a constant is still just a constant, and that term becomes 0. So it means that our partial with respect to x and then y is equal to 2x. A question that you might be asking yourself, well, you might not be asking yourself, but I might ask myself is, what happens if I did this in the other order? Does it really matter if I take x and then y or y and then x? Well, I'm not sure. Let's investigate. Over here, I'm going to use the same function, f of xy, but now I'm going to take my partial with respect to y first. So in this case, when I take my partial with respect to y, I treat x squared as a constant, and the derivative where y is the variable is just going to leave us with x squared, and the derivative of negative sine of x is just 0 because x was a constant. And that means that now, when I take my partial derivative with respect to x of this boring function, I get 2x. And that's it. Notice that this set of steps, they were different than those set of steps, but we ended up with the same answer. And this gives us Clairaut's theorem. This isn't just a coincidence. This will actually always be the case, that if we have that f of xy and f of yx are continuous, meaning there aren't any crazy gaps or weird things that might happen. If you have discontinuous functions, weird things happen. But if both of your partials are continuous, then it's always going to be the case that rearranging the order of the partial derivatives will yield equality. So taking the partial derivative with x first and then y is going to be equal to the partial derivative with respect to y first and then x. And you'll get to explore a little more of that in your problem set. Thanks. That's everything that I wanted to talk about today. Today we talked about partial derivatives and their graphical representations. We also talked about finding partial derivatives based on contour plots and computing higher order partial derivatives using Clairaut's theorem to be able to show us that these partials will always have equality, although sometimes taking these partial derivatives, it's easier to do one before the other, because some things might just disappear. Thanks!